Hello and welcome to the lecture Mathematical Preliminaries Part 1. We start with linear algebra. In this particular lecture, we are going to cover different aspects of vectors, matrices and eigenvalues and eigenvectors for matrices. We'll start the discussion with vectors. Now a vector is an ordered collection of numbers that represent a quantity with one or more components. In machine learning, vectors are used to represent data points, features, model parameters, embeddings, and latent variables, so on and so. Now, as a whole, what do you mean by vector? Vector is basically a ordered collection of numbers. That means here you can, in this figure, you can see that this is a vector. So this is x-axis, this is y-axis, and this is z-axis. And in x-axis, the value 2, in the y-axis is 3, and z-axis. So this vector, and in this three-dimensional space, the detection is this. This is a kind of geometrical visualization or interpretation of vectors. Now, in this three-dimensional vector, because you can understand the 3 dimensions. So one thing is possible, that in our machine learning point of view, just for example, what are the, you can say, just given a data points, let's say what is the measure of a cube, is height is 2, or z axis height is 4, this width is 2, and length is 3. So this is a kind of a vector by which we can find out a point in this three-dimensional space, and it can be represented either in a kind of row wise or column wise. It's a column vector, it's a row vector as per application demands. So this is called, in this particular example, the three-dimensional vector. It may be n-dimensional, and it has the 3 components element. This visual or geometric interpretation. So as a whole, that is a very simplistic idea about vectors. Now, what is the use of the vectors in our study of machine learning, generative AI? Now, intuitively, vector is used to represent a point in a space. In this case, this space is 3-dimensional space. It may be other dimension. If there is a 5-dimensional vector, so this space was 5-dimensional. So in general, vector has a 2 component. This is the magnitude and the direction. And these vectors are basically used from the just machine learning. That's the number of features. So we call it feature vectors. Features that describing an object or an image, a video, or whatever. Now, for example, a student can be represented as 21, 55, 86. What are these features? Well, these features, this is age, this is height, and this is the marks obtained in a particular course. So in this is just a very hypothetical example. In this way, the vector can be used different machine learning application. So in machine learning, vector represents one data sample. This is usual representation. Now, vectors can be used other machine learning data represent, such as word embedding in natural language processing, means flattened image in image processing. That means if an image is generally a two-dimensional, it's a kind of matrix format. But if we flattened it, just if we read row by row, so add the rows one by one, so it's become a vector, the one dimension space. So this is called flattened image. Then latent vectors in generative adversarial networks. So that are representations of some data representation or data points. So these are the basic use of vectors in machine learning and generative AI. Now some basic operations on vectors. Vector addition. Vector addition is basically element-wise addition. That x is equal to x1, x2, x3, y is equal to y1, y2, y3. X plus y means x1 plus y1, x2 plus y2. And this example 2, 3, 4, 1 is basically 2 plus 1, 3, 3 plus 2, 5, 4 plus 3, 6. If you see a graphical illustration of this particular concept, it's basically this. This is x vector, this is y vector, and this is y vector. Z is equal to x plus 1. Similarly, this is called basically a triangular method or head to tail method, and this is a parallelogram method where this z axis is basically y axis is there, x axis is there. So this is the basic operation on vectors. Okay. Some other important operators on vectors is scalar multiplication or scalar product. Let's say this is x and we multiply with del. Is delta with this. So delta x. It is a element wise multiplication. Delta x1, delta x2, delta x3. If this is x, basically it's this. The delta x is this stretched vector. If it is a 3, so it is. Or it is a 2, it is 2 times. Another important operation on vectors is called dot product or inner product. Let's say there is a two vectors x and y. X is equal to three-dimensional vector x1, x2, x3, and y is equal to y1, y2, y3, and x dot y basically x1 dot y1 plus x2 into y2 plus. So inner product result is scalar quantity. You can, if you add it up, then it's scalar. So if it's a 1, 2, 3 x vector, y is equal to 4, 5, 6. This is 1 into 4, 2 into 5, and 3 into 6. So basically it is 4 into 10 into 8. That's basically, if you see the geometric interpretation, if this is a vector, this is the v vector, and in between there is a theta, this u dot v, this dot product is basically this norm u, this magnitude of v, and cos of theta. So the dot product is one of the most important operation in machine learning because it measures the similarity and use the throughout neural networks and transformers. So using this dot product, we can get this kind of similarity. Okay. So these are the most other few important operations and useful information about vectors, which will be required understanding of our subsequent lectures. Next, go to the matrices. So few concepts like matrix representation, the basic operations like addition, subtraction, multiplication. What do you mean by matrix transpose? What do you mean by identity matrix, matrix inversion? So these are the few things that I'm going to list with the definition level. So when we represent a matrix, What do you mean matrix? Matrix is a rectangular arrangement of numbers organized into rows and columns. For example, here's an image. Image is basically a matrix of pixel values. So it is a fundamental concept of linear algebra and serves as a powerful tool of representing manipulative data. As I said, the matrix is basically an image, pixel values. For example, if A is a matrix, it's a 3 cross 3. This is a square matrix because number of rows and number of columns are same. And B is a rectangular matrix because it's a 2 by 3. That means number of rows is 2, number of columns is 3. Rectangular matrix. So first of all, what is the size of the matrix? Size of matrix is basically the number of rows into number of columns. So this is a 3 cross 3 matrix. It's a 2 cross 3 matrix. So matrix is widely used in machine learning, computer graphics, scientific computing, data analysis, and so on and so forth. For example, image represented matrix, as we said. Now, what is the basic operation? First of all, matrix addition. It's very easy, just element-wise addition. Dimension of the two matrices must be same. So this is the 2 by 2 matrix, another 2 by 2 matrix, and just A plus E, B plus F, C plus G, D plus H, and so on. Matrix subtraction is also very similar. That is its element-wise subtraction and dimension of the matrix. Next comes the matrix multiplication. Now, what do you mean by matrix multiplication? Multiply each row with each column. So, each row with each column. So, A into E plus B into G. This is the first element of the product matrix. Okay. Then C into D. So, C, F, H. So, C into F. And first this to this. So, first this to AE, B, G. This. So, this of F. So, A into F, B of H. So, this is the second element. And so on. This now this to this, C into E to D into G. Then CD to FH, C to F, D to H, and so on. One important thing to understand that for a matrix multiplication, column dimension of the first matrix should be same as the row dimension of the second matrix. If there is a 3 cross 4 matrix and there is a 4 cross 5 matrix, this is possible because column dimension of the first matrix is 4 and row dimension of the second matrix is also 4. So the product matrix, the dimension will be 3 into 5. So if A is a dimension 3 into 4, B is equal to 4 into 5, then this is the column dimension of matrix A and the row dimension of matrix B. These two are same. And what is the resultant matrix or product matrix? 3 into 5. So matrix AB will be 3 into 5 size. So that is the basic rules of the matrix multiplication. Now we have to understand what do you mean by transpose of a matrix. Now transpose means if row and columns are interchanged. So the transpose is obtained by interchanging its rows and columns. In other words, every row of the original matrix becomes the column in the transpose matrix. Every column becomes that's it. AB is a row, now it's become first column. CD is another row. Just this. If the original matrix the dimension n into a, then its transpose matrix dimension definitely n into a because these rows become columns and column becomes rows. When a matrix is equal to its transpose, A is equal to A transpose. That is called symmetric matrix. This is very important. This means the element in the ith row and jth column is equal to the element in the jth row and ith column. So Aij is equal to Aj. So this is a symmetric matrix. You can see 1, 2, 3, and this is 1, 2, 3. This again, you can say 2, 4, 5. So if you take a transpose, 3, 5, 6. So basically, this is a matrix. Now, another important concept of the matrix is identity matrix. Identity matrix is a square matrix in which all elements of the main diagonal are equal to 1 and other off-diagonal elements are equal to 0. It is usually denoted by I, capital I. So a 3 cross 3 identity matrix is basically look like this. The interesting property of this matrix is such that if we multiply a matrix with identity matrix, it remains same. And it's the commutative kind. Both way if you multiply. Next, some definition of the matrix. First, most important, what do you mean by determinant of matrix? Let A is a matrix, that ABCD is a matrix. And the determinant of A, which is denoted by date of A, is basically AD minus. That is the definition. Now, a rank of a matrix. The rank of a matrix is the maximum number of linearly independent rows and columns in a matrix. It indicates how much unique information the matrix contains. In simpler terms, the rank tells us how many rows and columns are not redundant and cannot be expressed as combination of numbers. That is very important. That let's say if this is 1, 2 and 2 and 4, these two rows. Now this 2 and 4 is basically, if you have a linear transformation, 2 into this row will be this. So we can say that this row is linearly dependent on this row. Then the rank of this matrix is not 2, rather 1. Okay, because this the linearly independent rows, number of linearly independent is 1, not 2 in that case. Next is a singular matrix. A singular matrix is a square matrix that doesn't have an inverse. In other words, if it is a matrix whose determinant is equal to 0. Just for example, this 1, 2 and 2 is a singular matrix. Now you see, now this is also a kind of matrix that if we calculate the determinant, 1 into 4 minus 2 into 2 is 0. So determinant is 0. It doesn't have an inverse. Now, very importantly, its rows and columns are linearly dependent. That was what we have just said in the last slide. Now this row, if you just make it multiplied by 2, you can get this row. So this row is linearly dependent on this. That means in our example, that 2 into 1, 2 into 1, row 2 is linearly dependent on row 1. So the rank is 1. And another important, rank is less than its order because it is 2 by 2 matrix, as rank is 1. So in our example, matrix A is 2 cross 2, but its rank is 1. Because there is only one linearly independent row, The second row is depending on this, and this is the second. Now it has a lot of implications. The system of equation represented by this matrix doesn't have a unique solution, because this, what we require, two linearly independent equations to find out two variables. That is required to get a unique solution. So that's why, because it has only one linearly independent equation, but number of unknown variables is 2. That's why we don't have. Okay. So this is another important. Next is the matrix inversion, and that is a very important concept. And inverse of a matrix, denoted by A to the power minus 1, something like this, is a reciprocal of the matrix, such that A multiply A inverse is equal to identity matrix. To get a inverse of a matrix, the matrix should be a square matrix, and it's a non-singular. Determinant is non-zero. Okay. So for matrix 2, for a 2 cross 2 matrix, there is ABC. A inverse is equal to 1 by this determinant of A into is D of minus B minus C. Sometimes it's called the adjugate of the matrix A. But if it is a 2 cross 2, this is the equation. So what about if it is a 3 cross 3? So matrix inversion of a some larger matrix 3 cross 3. Now let's say this is the 3 cross 3, 1 1 1 2 1 3, 2 1 2 2 4 3, 3 1 3 2 3. First of all, we have to find the determinant of A. So data of A11 dot this. A11 means this and this is. I am not taking A23, A32, minus A12. So this and this. This column, this row is not taken. A21, A23, A31, A32 plus A13. So this and this will not taken. A21, A22, A31, A32. So this is the determinant. If we find the determinant is 0, that will stop, otherwise go to step, because the determinant we cannot have matrix inversion. Now we calculate the transpose of matrix. So what is A2? That A11, A12, A13. Just this becomes the row becomes column and column becomes rows. Then we find the determinant of each of the 9 minors. Minors means what? So this is minors means this is the minors. This row, if we minus, this is A11, this is A12, this is 1 2, this row and this. So A21 is basically what? A12, A32, A13, this is, and so on. In this way, these are the each of these are 2 cross 2 matrix. Now these are the 9 minors of A transpose, each of which is a 2 cross 2 matrix. Then create the matrix of these determinants with alternatives. Name is A11 minus A21, A31, minus A12, A22, A minus 3, A13 minus A23. This is called adjugate matrix. Okay. The adjugate matrix is basically, and the inverse of the matrix is basically 1 by A adjugate. So this is the way we can find the inverse of the matrix. Now, another very important concept is eigenvalues and eigenvectors of the matrix. Now, if we consider a matrix transform, that means a projection matrix, the most of the vector change with both length and direction if the matrix transposes the space. However, some special vectors keep their direction, maybe in reverse is also possible, so keep their direction intact or reverse it under this transformation, and these vectors are called eigenvectors. Okay, so for x square matrix A, an eigenvector V satisfied that this matrix A, if we multiply it, so it basically transforms this vector. It basically what it just scaled either in the same direction or in the reverse direction, but direction is not changed. So if V not equal to 0 is a eigenvector and lambda is called corresponding eigenvalue. This is the basic idea. The equation says that applying A to V, so when this matrix is to transform V, only scales it by lambda, so its direction remains unchanged, except that the negative lambda replaces the direction. So this is the basic understanding of eigenvectors and the corresponding eigenvalues. Now, what is the geometric interpretation of this? Let there is a matrix A 3 0 0. This matrix, if it was a linear transformation space, such that most of the vectors change the direction and magnitude. But if we consider the V is V, let's say V1 is equal to 1 0, basically exact. And if we multiply this to the matrix A, this matrix, we can get that 3. So that means the Vi is not changing the direction. If you see the figure here, this 1 0. Now if you this matrix we basically transform this space, you can say V0 becomes V1 transformed, that is the direction intact. Same as if V2 is basically 0 1, this is y-axis. If you do this transformation or a kind of transform, you can say 0 2. It also doesn't change its direction, but only stretched by 2. You see here that this y-axis, initially it was this, now it is stretched by 2. So these two vectors 1 0 and 0 1, they are not changing their direction, but they change only stretched by some value. So these are eigenvectors, and the what factor they are scaled, this is 3, this is eigenvalue, corresponding eigenvalue, this is 2, this 2 is corresponding. But if you consider another vector, this 1 1, these vectors with 3, now you could see these vectors become 3 2, multiply this. So now if there is a change of direction, so this is not the eigenvector. So V3 is not eigenvector matrix. V1, V2 is the eigenvector. So that is the basic interpretation. So V2, V1 and V2 are the eigenvector matrix. and V1 eigenvectors with corresponding number. So this is the basic understanding. Now how to find for a square matrix A eigenvector V satisfied is that we have seen, and since V not equal to 0, eigenvector is a corresponding number. This is the matrix, and we now A of V is called lambda V. So lambda I is basically identity matrix. We can easily write it. I is identity matrix, so we can write this. Now since A minus lambda I into V is 0 or equal to 0, so A of lambda is a singular matrix because V is not equal to 0. So date of A of, so determinant of this 0. So this equation is very important, and this equation is called characteristics equation of the matrix A. Now if we put it in this, we can have this, and there is two values of say lambda 1 is 3 and lambda equals 2. These two are eigenvalues. If we first take lambda 1 is equal to 3, and we put lambda 3 is the eigenvectors and put it here, we can get this equation, and we find x2 is equal to 0. That means V1 may be 1 and 0. Is a valid eigenvector for lambda. Similarly, when we put this lambda 2 is equal to 2, we can get V2 is 0, 1. This is x-axis. Basically, this is the y-axis. Valid eigenvector. So that we can get these. So in this lecture, we first introduce vectors, definitions and basic operation. Then we understand what is the very simple understanding of matrix, represented basic operation and matrix transpose and inverse, and then the concept of eigenvectors, definition. In the next lecture, we are going to understand the basic probability. Thank you very much.